Hello everyone, and welcome back. Now, thermal stresses. I mentioned these earlier and said that they come when something is restrained. If it's trying to expand and it can't, or it's trying to contract and it can't, there is a stress that forms. Now, why does it form? Well, it's because if it's trying to expand, trying to get bigger, something has to push on it to keep it from getting bigger. In this case, that would be the wall. The wall is pressing on it, and so a stress forms. Now the walls aren't moving, it's just that this is trying to get larger, it can't, and so it feels that stress. Um, you know this because if you ever try to put on a piece of clothing that's too small, you feel it. That clothes aren't moving, they're not trying to squeeze you, but you are trying to expand into something that is not big enough to hold you, and you feel the stress. I remember, I still remember when I was probably like 13 or 14, and I accidentally switched and got my like 6-year-old little brother's pair of like khaki pants. I thought they were my shorts. I tried to put them on. I was so confused at first. I'm like, why are my shorts so small? I was like, oh no, they're my little brother's pants. They're not a pair of shorts. So, oh man, funny memories. Now let's look at this. So thermal stress right here. It's using this equation. Now, where does this equation come from? Well, stress is equal to our modulus elasticity times our strain. What we learned last time is that, oh yes, this thing right here, that equals the change in length over my initial length, which is actually a strain. Usually we put it as a subscript T just to say it's thermal strain. So this is equal to a thermal strain. So all we're doing here is we have our same strain equation. We just have a new version of strain. We have something else that's causing the strain this time. Now, I mentioned that this can lead to failure if you're not careful. And I want to show that right now. So we're going to do a little bit of an example here. There's another example after this one, but I want to go ahead and show you an example. Now, last time we had a 15-meter long piece of copper, and it had a change in temperature of 49 degrees Celsius. We're going to forget that change in temperature for now, and we're just going to leave it as we're trying to figure out what it is. The big issue with this one is that eventually it will fail if it reaches 200 megapascals. It's actually 220. For now, I'm going to leave it at 200. And for the sake of nice numbers, I'll make this a 0. So, what's the thermal coefficient expansion for my copper? Well, it's going to be equal to 16.5 times 10 to the negative 6. Okay, 16.5 times 10 to the negative 6. And that will be this. And what is our modulus elasticity? Well, that is around, I'm going to just once again round, say 200 gigapascals. It's not quite correct, but it's going to be close enough for what we're doing right now. So I want to see at what point will this fail. We got 200 megapascals to start, and I want to see when it will fail. And the second question is, do I actually need to know this length? Well, I actually don't. It doesn't matter at all. Because I'm not trying to calculate how much it stretches, just when it reaches a strain that will cause it to fail. So I plug everything in here. I say, okay, 200 megapascals is equal to 200,000 megapascals times 16.5 times 10 to the negative 6 times delta T. Okay, so the 200s cancel, and I got a 1 over here and a 1 right here, so that's 1,000. And then I multiply that by 16.5 times 10 to the negative 6, which gives me 1 is equal to 16.5 times 10 to the negative third, delta T. And divide this over and I get 1,000 is equal to 16.5 delta T. And then if I wanted to, I could round this a bit. I'll go ahead and I won't round it. So what is 1,000 divided by 16.5? Well, let's pull my handy dandy calculator. 1,000 divided by 16.5, and I get 60.6. Okay, so 60.6 is going to be equal to the change in temperature required in Celsius to lead to failure. Now remember, I did round some things. This is not quite the modulus elasticity. This is not quite the failure stress, but it's close. Now 60.6 degrees Celsius, that is a lot. That's fairly a lot. However, it's not honestly as much as you'd think. You can see that in nature. 0 is freezing, 100 is boiling water. I'm thinking, well, nothing gets to boiling. You're correct. However, you can have a very, very hot wire that suddenly switches and it gets very, very cold. So if you were to take a wire, stretch it, get it in place on a very, very hot day, and then suddenly on a very, very cold day, like in Michigan, well, it might lead to it snapping because it's too tight. That's why most of your electrical lines are never super tight. They always have a lot of slack in them to prevent this. Okay, so I just want to show you that these temperatures where it will cause failure are not unreasonable. They're not crazy, at least for things like copper. So you have to be careful in how you're setting things up. So I hope this helps you. Thank you all for listening, and I'll see you all next time. Have a wonderful day. Bye-bye.